generalized SYZ mirror symmetry for the resolved conical.
Thanks. Yeah, so I guess I'm going to talk, as you just said, about generalized SYZ mirror symmetry. I guess it's like probably pretty bad form to start a talk with a disclaimer, but I'm going to do a lot of things that are bad form in a math talk in this talk anyway. So disclaimer, there's a lot of physics in this talk, in particular in this section 3, and I am not a physicist. So I was very grateful to have the opportunity to learn some of this stuff, but I'm still pretty shaky on it, so if anybody, I guess feel free to correct me if I say something that is wrong. But I may say things that are mathematically sketchy. All right, so yeah, so I guess maybe not very many people here know, or maybe some people know and some people don't, the general sort of SYZ philosophy for drawing mirror symmetry. So I thought I'd start with some sort of introduction to that and go from there. So yeah, so the first part of this talk will just be some introduction to SYZ mirror symmetry, and I'll introduce the goal of the talk. The second part will consist of me talking about this Lagrangian conormal in this resolved conifold, explain how we get that, and talk about its quantum protected moduli space, which we're going to be interested in. The third talk is where things get, the third section is where things get very with Chern-Simons and topological strings and quantization. And then finally, I'll try to say some words about what the mirror symmetry statements we can make from this construction. I didn't have time, or I don't have time to talk about sort of the more homological statements, like things involving like Fukaya categories or DB-Co, blah, blah, blah. But that's closer to what I do in my research. I mean, that is sort of what I do in my research, so I'm happy to talk about that after the talk to anyone. I've already promised some people that I'll say some words, so yeah, so those are missing, but do feel free to come talk to me afterwards about them. Okay, so the general sort of setup here, or the goal, is given a knot K, we obtain a mirror space to this resolved conifold we saw. So it's the total space of this bundle over P1, using some sort of SYZ philosophy. Okay, so I guess I should say who these people are. So this is Strunger, Yao. Okay, so so the SYZ generally says that if we have X, and I guess classically we want it to be Calabi-Yau, or maybe we just want, in more sophisticated versions, you just want Kähler. But given some Calabi-Yau X, say, we realize a mirror Y by probing X with L. Okay, so L lives inside X, and this is just some special Lagrangian. Okay, so special Lagrangian, so you know what Lagrangian means. Special just means that, okay, you have this non-vanishing volume form, and it's going to take constant argument on L, is one way to say it. Okay, so we probe X with L, and in fact, so we say Y, we can look at Y as a moduli space of L, or sorry, of X, no, correct? L plus extra data. So normally this takes the form of, say, like flat unitary connections. Okay, and so people have kind of gone very far with this. Oh, okay, so then what does mirror mean? So mirror, we should have, okay, so I guess the physicists say A branes and X correspond to B branes and Y, and vice versa. So these are holomorphic. You can think of these as holomorphic, or like complex submanifolds rather. And then these are Lagrangians, roughly. Okay, so there's a lot of different sort of formulations of mirror symmetry, and there's no real, like one true formulation. Normally, I guess I would say something more like we have like some Fukaya category over here, which is going to correspond to like some derived category of coherent sheaves, blah, blah, blah. But really, I mean, the essential thing is the symplectic geometry of one corresponds to the algebraic properties of the other, and vice versa. Okay, so, fine. So, usually, we want L is a torus. And then SYZ, like, we'll say, I mean, there's some paper called, like, mirror symmetry is T-duality. But, so this stands for torus duality, and what it's saying is that both of these spaces are going to, like, emit fibrations by special Lagrangian tori, and they're both going to be over the same base, and blah, blah, blah. But this generalized SYZ, so we say it's generalized because we're not going to probe it with probe your space with the torus. It's going to be this sort of Lagrangian conormal associated to the knot. So I guess that was not really talked about in the last talk, so let me do it really quickly. Okay, so recall to a knot K, we associate this Lagrangian conormal, but here this is going to be living inside of T star S3. And so now we want to sort of pass this through the geometric transition. So to get some LK, okay, so this is abusive notation, but living inside, say, do I have it written down? Okay, yeah, so I'm going to call this thing Y. YG, one second. Yeah, so I want some Lagrangian living inside this resolved confold, and then T here is going to be the Taylor parameter.
So I also want to call it Y later maybe, but you have already used Y for
Have
mirror.
I? Yeah, okay,
Maybe
so
like a non-script Y
yeah.
or something.
You don't want to call it X?
I want to, okay, so I want to keep my yeah, so probably I should have put in,
You can switch X and Y maybe.
yeah, so here I think I should switch X and Y.
No?
No?
Okay.
This is
Okay.
No. Well, no, I do want to switch X and Y. Sorry. Well, okay, so the problem is that, like, once you start doing mirror symmetry, like, theoretically you should have, like, all these, like, things going both ways, so it doesn't really matter. But let's see. Okay, so Y here for me is definitely going to be my A model. So I do want... Sorry, this really doesn't matter to anyone, like, who just wants to get, like, ideas, but just to keep things straight, yeah. Okay. Yeah.
On one.
Where is it?
X by probing Y with L.
Probing. Yeah, thank you. Okay. Any other questions or notational confusions before I go on? Okay, cool. Right, so what was this? So let me just remind you really quickly. So this was just going to consist of, there's like, oh god, I don't necessarily, okay, so X, these are very bad letters, so I use them later. Okay, I don't use A and B later, but it's also not so great. So just points in your knot, and then B in your cotangent space, restricted to your knot, such that B defeat, like B annihilates your tangent space here not. Okay? Fine. So we have a problem now because this lives over the 0 section of your S tree, right? And when you do this geometric transition, that's the part that you're sort of touching. So really we have to, what we have to do is deform L off itself slightly, and then we can pass through to get to get your Lagrangian over here, still be Lagrangian, and still will be like identical topologically, but now it will not live over the 0 section. Okay, so how do we do that? So we push L. Okay, I'm going to suppress the K for now, but the K is lurking everywhere that I'm going to do. So we push L off itself by d theta, this is just your one form machineries for each one. Okay.
Are you trying to get it to be off of itself or off of the 0 section?
Off of the 0 section.
Okay.
Yeah. Yeah. Sorry. Thank you. Yeah. Yeah. Thanks. And I think Maxime might talk more about this. Okay, but then that's fine. And then from there we can sort of get this L and sitting inside the resolved conifold that we want. Sorry, so I know that was pretty sketchy, but really all you have to, I mean, it's a sort of a simple thing. You just take a knot, you look at this Lagrangian conormal, you want it to live inside your resolved conifold instead, because that's what we want to realize in mirror space to. And then you can just do it by again, like pushing the knot off the 0 section and seeing where it goes under your geometric transition. Okay, right. And so that's good, because now for every knot, we have a candidate Lagrangian that we can probe the conifold with. So we now know that this L is topologically the same as S1 times R2, and so in particular we have that the first Betti number of L is equal to 1. Okay, and so now what we want to so recall that sort of the SYZ philosophy means that we have to start thinking about the moduli space of L and its deformations as special Lagrangians. And so there's a theorem by McLean, I don't know, that will say that moduli space of L with flat one connection is one-dimensional.
McLean's theorem only applies to compact special Lagrangians.
Yeah, so all the papers cite it though, so I'm assuming that you can use it in some form.
But there's sort of another issue.
Yeah?
I mean, maybe, I don't know.
Okay.
Yeah, I can say something and we'll see if it makes sense. So
Okay.
it applies to special Lagrangians
Yeah.
and deformations of special Lagrangians. On the other hand, we don't have like, is it special, is it not special, I don't know. But there is sort of a more naive way to think about it, is just that, if you just want to kind of classes of deformations up to Hamiltonian isotopy near the given one, then of course we all know that like if you have a C1 small perturbation, it's a graph of the function, and then, up to Hamiltonian, it's exactly this B1. So in that sense, it's kind of more trivial. And it doesn't have to be special or whatever, and but in the original physics formulation, of course, you want this, this kind of special things, and then there is kind of this conjectures, right, about every Hamiltonian class having unique kind of up to some surgeries and stability and whatever having special representatives, but you can kind of maybe suppress all of that and wait.
Yeah. I mean, okay, so maybe this is not okay. I'll just say or.
or be more slopey.
Or something, yeah.
I don't know.
Or, yeah, or something. Sorry. Yeah, so it doesn't, yeah. I mean, so maybe an illustrative example is if we're just thinking about like sort of the equator, and P1, which is, and some bundle over it, which is like going to correspond to the unknot, in this picture. Okay, and again, so you really shouldn't think about the equator, you should think of something slightly off the equator or whatever. But we can sort of like move it that way. Yeah. Okay, but so it's one complex dimensional. Okay, and then let me say one more thing for people who like have seen the XYZ star before. So this is sort of strange because normally you want, if you have some sort of like complex torus, your moduli space is going to be like, okay, so if it's like Tn, then it's going to be like n-dimensional and you have some nice like, then you can start doing this vibration thing. Here the vibration is much harder to see because it's only like one-dimensional. Okay, and then we're going to parameterize this by x, which is going to be equal to r plus I theta. So this is in C. So r measures shift along d theta, and then, oh sorry, so there's two thetas here, but maybe I want to call this rho. And then rho measures, yeah, your U1 connection. Okay. So that's fine, but then we also here need to consider the sort of quantum corrections to our moduli space. Meaning we want to start thinking about how this thing might bound holomorphic disks. So we're going to introduce this Gromov-Witten disk potential, which I will write down. And so this is going to depend on x and q. Okay, so x is this parameter, and then q is going to be equal to e to the negative t. So this encodes. So you should think about both of these as like kind of relative homology classes, like we saw the x and the q before. Right, but so this Gromov-Witten potential is going to depend on both of these things. Which are both sort of measuring the area of these relative homology classes. Sorry, so you should think of both of these as complex numbers, is what I mean. Okay, and it's going to be some counting things. Oops. Sorry, this is R. Okay. Yeah. Questions? Okay, so this is more. So this is more information. So this is what people call like sort of encodes like the quantum corrections to L. Yeah. Okay, so now we want some sort of space that encodes all of this information in its classical geometry. And to get that space, now we're going to go into the land of physics. And things are going to get, yeah, I mean, I'm not going to have the best justifications for things, but so I guess this is now section 3.
Maybe I should say that.
Yeah, please say something.
No, I just wanted to say that I'll discuss this Gromov-Witten potential. This is like essentially the main thing in my talk, I guess, or something like it. So we'll see like some kind of definition of it from the holomorphic disks. So,
Yeah. Okay. Yeah. So this is going to be sort of the bulk of my talk. So this is this Trent-Simons section, topological strings and quantization. And really what this is going to do is kind of give us coordinates on some, so getting coordinates on a mirror space. And in fact, it's going to be Claudio. Yeah, okay, so let me point something out. So right now, like, if you sort of just don't, if you ignore sort of the quantum corrections or whatever, you can just be like, okay, so you've now written down some moduli space of this Lagrangian, it's one-dimensional, like, sort of like naively, like, if you think about what I said about SYZ, then why aren't you just like happy? But that's kind of no good, right? Because you also need to encode these quantum corrections. I mean, especially, what do I want to say more about that? Yeah, maybe I'll leave that for now. I mean, somehow, like, C is not the mirror to, like, the resolved conifold. So, yeah.
Well, I mean, it's a local description, right?
Right. It's a local description, right? But the point is that, like, it's not, yeah. You don't, and particularly you will not get this correspondence between, like, brains here, and so, yeah. Okay, so, recall from the previous talk, we can use Chern-Simons to get information about open strings on YT. And that's good because these sort of things look like open strings if you kind of, or planar open strings rather. So how are we going to start to do this? Okay. So the first thing we need is some sort of partition function we can start doing physics with. Okay. So we okay, so sorry, let me just write this. Okay, so we want some sort of like not partition function that we can start extracting data out of. So again, this is going to depend on x. It's going to depend on q, but I'm probably going to start suppressing q. This is just some sort of formal parameter you should think. And it's also going to depend on this gs, which is just going to be equal to some like string coupling constant. If you know some physics, this is going to play sort of the role of h bar, I guess. And then we're going to sort of start thinking about what happens when that goes to 0. Okay, so yeah, so now maybe this is going to come out of nowhere, but we can write psi k of x, again I'm going to start suppressing things, as the sum for like symmetric representations of these Hamfly polynomials which depend on your string coupling constant and your q times e to the mx. So this is some like weighted sum of expectation values of some observables in your Chern-Simons theory. But this, like I said, this is sort of coming out of nowhere. Perhaps a more enlightening way to think about this is let me just write it, and then I'll explain why you might want to write something like this. Okay, so another thing you can, okay, so it's non-trivial that these things are, well, it's very non-trivial that these things are equal. But you could also write your not partition function as some product, okay, so this is some Gromov-Witten partition function, which counts like open strings with you have one brane on your, sorry. Yeah. So you have one brane on your Lagrangian, like n branes on like some zero section. And then you're gonna divide out by your Gromov-Witten partition function, which just counts like strings on your resolved conifold. So both of these, like I said, are very like mysterious objects, and I don't really have enough time to like talk about why they show up. I think like the takeaway for me is that you can get. So this is like some Humphrey polynomial. So this is just some like non-invariant. So the point is that like the string theory sort of knows about non-invariants. Like how do you get this thing? Well, you can just like start integrating. Sorry, I forget the exact words for how you get this thing. Yeah. I mean, does anybody who actually knows anything about this want to say anything more about these partition functions? Because, yes.
Can I, so
Yeah.
if I understand correctly, so the moral of John's talk was that there is some, in the closed string case, when you don't have a torus and associated Lagrangian, you have some Chern-Simons theory of S3 that is basically equivalent to kind of Gromov-Witten theory on this resolved conifold.
Right.
And then if you introduce the knot on the Chern-Simons side, you get the Collet-Humphrey polynomial, and
Right.
that same correspondence makes that somehow, in some sense, equivalent to the open Gromov-Witten potential of this co-normal Lagrangian that you associate to the knot.
Right.
So that's why these two different mathematical objects should be related.
Yeah. Right. I mean, I think, yeah, the way I sort of understood like the flow of information is that you can actually, which maybe this is wrong, but you can actually compute things, like Chern-Simons is like somehow more computable than the open strings or the closed strings things. And the topological string stuff on the T star S3 is equal, like you can show that that's equal to some Chern-Simons with appropriate constants. So then you're very happy because you can start actually computing over on that side of the geometric transition. But I could be wrong, so.
It works both ways. I mean, sometimes the Collet-Humphrey polynomials are hard to compute, but you can compute something on the through our augmentation stuff on the other
Right.
side.
Yeah. Okay. But yeah, so now we have this like very mysterious partition function. And we're gonna start using different expressions for this thing to get out some coordinates on our moduli space. So what are we gonna do? So I guess this is an idea due to Witten, who, yeah, probably a lot of these ideas are due to Witten, but in particular, this one. If we think about, or rather, what do I say? Okay, so let me back up a little bit. As far as I understand it, like now the goal is to start doing some quantization thing, which is going to be like start like taking these coordinates, like find canonically conjugate coordinates and start like regarding them as operators on some vector space, blah blah blah, to sort of get the coordinates. So that's what we're gonna do via this Witten thing. Okay, so Witten says like some contribution. Short strings beginning and ending on this Lagrangian can be understood with GL1 Chern-Simons theory. And that's good because this is not so hard. GL1 Chern-Simons theory, that's just going to be like theory of like flat connections of GL1 Chern-Simons theory. Okay. Yeah, some flat connections on your thing. So let A be connection, and then we can write down coordinates. Which do I have? Yes. A lambda, A mu, and A t. So here, so this is going to correspond to, so there are 3 coordinates. Lambda is equal to sort of the S1 direction. And then mu is equal to sort of, I think this is consistent with how other people have done them. I forget the word for this, meridian? Meridian. Yeah, but how to make that an adjective?
No.
Yeah. Yeah, and then, so, and then T is the other one. Right, and we can choose coordinates. So AT is equal to 0. And then what we can say is that, okay, so then the Chern-Simons, okay, so this is the Chern-Simons action, is going to be, after you like do some integrals, do some clever things, you get that this is just going to be equal to the integral over R of P x dot minus x P dot, okay, yeah, so x dot is equal to dx dt, etc. Okay, so if you know any sort of like classical physics, this is equal to the classical action x dp minus p dx. Okay, so the physics heuristic tells us that x and p are canonically conjugate. Okay, so sorry, let me back up and say some words about this. Okay, right. So now you might be unhappy with me because it seemed to have 2 x's on the board, and that's like a fair complaint. But you'll note that the x's are actually measuring sort of the same thing. You know, like somehow the x coordinate you can get if you have a flat connection. The x coordinate will tell you like where you are sort of in this moduli space. The p thing has sort of come out of nowhere, but that's okay. I mean, we know we want a p for whatever sort of mirror we're going to write down. Yeah, and then.
How does the A give rise to the?
Oh, sorry. Thank you so much. Yeah. Wow. Yeah, I just omitted like a very key thing. Yeah, thank you. Yeah, sorry, I said like, okay, these things correspond to these directions, but I should have said the word holonomy. So x, thank you, is equal to the holonomy around of A, P is equal to holonomy around U of A, and that's the loop I drew here. Yeah, thank you. Yeah. So given the connection, then you get these coordinates. Yeah. Yes.
Sorry, Thomas wrote this Chern-Simons action as like this integral of ADA.
Yeah. So that's I'm skipping like about 7 lines here, but this is this like ADA minus or plus like 2/3 A wedge kind of thing.
Same thing.
Yeah. It's the same thing. You just like do out everything, and because it's one-dimensional, like things simplify like quite a bit. Yeah. Yes.
Well, you have a t in the x dot.
Yeah.
It's dx dt, and then you have another coordinate t over the same t.
Yes. Yeah.
So that's a direction. So if this actions locally, it's like tars times an r, and that's
Yeah.
the direction of the t, and it's also the direction you are integrating for that r, I guess.
Yes. Yeah. Thank you. Sorry. I mean, really, like, I think like the point is like this equation is supposed to make sort of the physicists very happy because they like thinking about canonically conjugate variables. But but yeah, it sort of comes out of nowhere. But okay, so what does canonically conjugate mean? Well, then we should, so the philosophy then tells us, okay? So then we should think about P as the momentum in sort of the quantum sense, and then X is the position. So that's why maybe you chose those variables. And so then, so this should look like something G dx. And in particular, you should have this relation. Yeah. So this is part of the whole quantization scheme where like now your position, you start thinking about non-commutativity of some operators, which previously just looked like coordinates. So then, what we should do, so then should write P. So we should think about, okay, so we have these things, we're thinking about them as operators, and then what do the operators do? Well, they're going to act on position functions, which here are like, quote, our wave functions. So we should write that P psi k of x is going to be equal to G sub s d dx of, okay, and then now this just looks like some like kind of differential equation. And so particularly we can use this like so-called short wave asymptotic formula. So okay, so the idea here is that we're going to get some correspondence between, or some relation between x and p in term by sort of expanding this thing out in two different ways. So yeah, so the short wave asymptotic formula tells us that we have psi k of x is equal to the exponential of the integral 1 over gs, this period integral p dx plus dot dot dot. And then these dot 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 terms are, I think big O, yeah. Big O of 1 in gs. Okay, so recall that we're going to take gs going to 0. So essentially, like the leading terms are going to dominate. So this is sort of a valid thing to do. Yeah, and you get this straight from that line. Okay, but we also have another expression for psi k. So we know also that psi k is going to be equal to some like, or rather, the exponential of some counts of strings. And okay, so I guess I didn't write out this formula exactly, but maybe you can believe me that you're going to start weighting these counts of strings by the genus, and then that's going to give you sort of like higher power. So you're going to get gs to some factor, which is going to be positive if your genus is greater than 0. So this is okay, yeah. So this is going to look like exponential of 1 over gs times this Gromov-Witten potential, which I've erased, xq plus dot dot dot, and these are again have some factor of gs in them. So okay, so then we say okay, gs goes to 0. So then we equate 1 over gs, this integral of p dx, with this wk, yep, 1 over gs wk x to q. And so we end up with p is equal to the partial derivative of wk with respect to x. Okay, so this is a very nice equation. And it's going to show up again in Maxime's talk in a more sort of direct way. This is sort of some like physics trickery with like expanding some things, and it's kind of hard to see what's going on here geometrically. But it's okay, because now we have this nice equation.
some point did P turn back into a function from being an operator, or is it?
Yeah, okay, so this is kind of a subtle point. So really what you're gonna end up getting is in fact, okay, so I'm gonna say, okay, you're gonna get a Riemann surface as the mirror. But in fact you actually get a quantum Riemann surface where P is going to be an operator and a coordinate. But I like-
It turns back to a function when you take this short wave asymptotic. So you somehow you can forget about where it came from, but if you do some kind of ordinary quantum mechanics, then you can somehow try to express the wave function as this thing, and then the first order term is given by the integral of the action.
Or another way, when you set GS to 0, you take the semi-classical limit.
Yeah, exactly. Yeah.
Mm.
So this is the semi-classical in some sense. So at that point, so this P, when P is an operator, that's kind of slightly more advanced. So I think now we have kind of even a normative understanding of this, but here not. But then somehow when you go back to this potential, then you took the semi-classical.
Sure, okay.
Then it's again at that.
Yeah. But there is some story in which like you actually do get like some like so-called quantum Riemann surface as the mirror, no? Like where you sort of remember that P is an operator. But yeah.
So just make sure I understand. So in this board, when you introduced the concept, you started with Chern-Simons theory.
Yeah.
And so here you use this fact that the Chern-Simons should be given by the scholar Humphrey, but it also admits a description as some concept, some Gromov-Witten potential.
Yeah.
That gets used here.
Yes.
Okay.
Yeah.
And that was like physics magic, or
Which thing? The partition
to get
function
from
thing?
this side to that side.
Okay, so there's nothing happening. I mean, so here, this is a separate sort of, this lives by itself. This has nothing to do with this a priori. And in fact, the information is coming when we equate both sides of the expansion. Yeah. I mean, I would call everything in this talk physics magic, so, but sort of especially that, yeah.
But what's in that corner is kind of what happened this morning.
Yeah.
Sorry.
Okay, yeah, well,
But also you wrote this, that the psi k is given as this Gromov-Witten
yeah,
thing.
yeah.
So then you expand the Gromov-Witten and you
Yeah.
get the leading term. Right?
Okay. But this is, okay, so this is somehow nice though because now we have some expression for P in terms of Q. And okay, so I guess I'm almost out of time, but let me say, like, why the hell any of this gets us anywhere. Okay. So this tells us that the quantum corrected moduli space of L is okay. Cut out by some equations. One which locally look like P is equal to this x. And so we write this as, okay, so maybe we want to call this x naught. Well, that's terrible. So if we call x to be the quantum corrected moduli space, we write as x is equal to the curve, this is a capital X, ak of x, p, q equals 0. In fact, you don't want to take these things to be. So this is going to be some curve which sits inside C star cubed. Or, okay, so this is some mirror. Or you can consider, if you want it to be Calabi-Yau, for example, you can say,
Sorry,
we
what
just,
is X?
sorry, what is
that
X?
capital X?
This is a capital X, yeah.
And
This
it's
is a
set of-
lowercase x. Sorry, this is supposed to be back to consistent with my original notation.
Okay.
Some brackets.
Yeah.
Yeah, that's
Yeah,
fine.
fine. Okay. Yeah, okay. I'll put brackets. Sorry, it's kind of sloppy. Yeah. Or okay, let me do this out. So u v e dx. Or you get this hypersurface on this larger thing. X. Okay.
Isn't that what X is actually?
What?
The mirror is that last thing that you had there, right? Yeah,
Well, so
not-
so
not
both
the
of these are
singular.
going to have the same information, I think.
True, but they're different.
Okay, fine. So you don't want to call this X.
It's like the singular set of.
Yeah. Yeah, okay. I mean, I'm happy to just call this X and say, like, this is also a thing. Yeah. I mean, okay, sorry, let me wrap up and then I can take more complaints and try to say words.
Is your bottom one like a resolution of the top one?
Is the bottom one some resolution with, I mean, this is just like some conic bundle, right?
Yeah.
So, okay, I mean,
Is it more smooth?
is
The
it more
top one can be
smooth?
completely smooth.
What's that?
The top one can be completely smooth.
This one can be completely smooth. It will be smooth in the case of the unknot, for example. I think the real point is that you have this statement about, like, if you want to formulate your muosymmetry in terms of branes, sort of you want to do it on this one, just because there's sort of enough dimensions for the branes to live in. So let me say what I mean by that, or let me say what I mean by that for like exactly one specific brane. Okay, so recall that we should have A branes on YT corresponding to B branes on X. So in particular, so for example, we can talk about like where LK is sent, because LK is an A brane on YT, and so LK corresponds to the line or the points u equals 0, so that gives you the arbitrary. Sorry, this is not quite right. I want to say we take x naught, p naught, such that or this AK, e to the x, e to the p, q is equal, or e to the x naught, e to the p naught, q equals 0, then we can consider this like I don't know what I want to call it, just m is equal to e to the x naught, e to the p naught, q 0, v. So it's this sort of like line above x naught and p naught. And the point is that now the moduli space of M, like the classical moduli space of M within X as a B brane exactly encodes the information of LK. Yeah?
So you're fixing x naught and p naught and
then
for solutions in Q, or what are you?
I'm fixing x naught and p naught. I'm saying this is the line that's sort of like, okay, so we have this thing kind of living above 0, okay. I'm saying, okay, fix x naught and p naught such that they lie on this thing, and then
For fixed Q, or?
for fixed q, yeah, sorry, q here is, yeah, we're fixing q throughout here.
Okay, great.
I don't say anything about when q goes to whatever. Yeah, q is just some formal parameter. For fixed q, but then you're also fixing x naught and p naught, and you're saying, okay, but then I can look at like sort of this branch where like u equals, so I know this thing's equal to 0, so I can say like, okay, like just look at now we can vary v, and this gives you like some sort of one-dimensional family, or one-dimensional V-brane. And then we can say, okay, so the moduli space of this V-brane, the classical moduli space of this V-brane within M is going to be like how we can like vary x on and p naught, or x and p rather, and that like is exactly the like through this whole thing, that's exactly the quantum corrected moduli space of LK. What other information can we pass between the two things? Okay, well, so note that like the period, by construction, the periods here, so these like PDX things, correspond to some topological string. Amplitudes here. It's like, I mean, this, I had the equation written on the board, and I erased it. Yeah. But we actually expect more. So like sort of the interesting thing here is that like we can just sort of look at this thing and we can say like, okay, there's an obvious sort of like V-brane which should correspond to this Lagrangian. But like mirror symmetry tells us that like in fact for every like Lagrangian, every A-brane over here, we should get some V-brane over here, which is sort of like a very strong statement. And I don't know how we can actually prove that.
Right.
So, yeah, I guess I'll end there because I'm 5 minutes over anyway.
Any questions?
Yeah.
So like maybe on a good day I know what a quantum curve is.
Uh-huh.
But is there like a quantum version of X, you know, the thing that ended up being called X?
Is there a quantum version? Yes, I think so. I can point you to a reference. I don't think I can say anything smart about it.
Oh, okay.
Yeah.
What's the reference?
So I think that shows up in, it's one of these 3 papers. Let me look and I'll tell you. Yeah. Yeah.
I mean, we can eliminate 2 of them.
Okay. All right. So. Yeah.
Yeah, we're also working on something like this.
Okay, so yeah, I think I don't know the quantum version of X, but there is, you know, there is this quantum A, right? And so that's an upgrading this equation operator.
Right. Yeah. Yeah.
And then I think we have 2 ways of describing this quantum system on which this linear equation should somehow act on that side. So one way is somehow I cannot describe, and try to describe to say that this is the B model topological scheme on this X, right?
Mm-hmm.
And that somehow reduces to that's what they, I mean, Jan can help me if I'm saying something wrong, but they reduce it to some kind of fermion moving around in the surface, and that gives you it's governed by the full wave function, and this is the operator equation, sort of the Schrödinger equation. The other way is around this D module, that should then be interpreted as, instead of this thing, you take C2, C star 2, whatever it is. And then inside this C star 2, there is this curve which is a Lagrangian. And now you're supposed to do a model topological string with 2 grains. One is the curve, it's Lagrangian, and then this kind of co-isotropic space filling grains, full one. And when you do that, then you get somehow this operator upgrade from the co-isotropic grain, and then the rest should be. But to me, this is, I don't know, I mean, this is things I don't fully understand. But maybe the upshot is that this quantum curve, or the operator equation for you can also now, I think we can give it a purely somehow enumerative meaning. Also the upgrade of this operator, so counting homogeneous curves.
At infinity.
At infinity. So, I mean, I don't know. Yeah, I mean, you can find it from infinity. But the interpretation is some kind of normative thing.
Yeah.
To make sure I understand, so
Yeah.
in the construction of the mirror, so you're saying the mirror is locally cut off by some equation P equals dw dx?
Yep.
And then, so if we say it's a zero locus of a polynomial, we call that polynomial the A polynomial, and then, so I could indeed think of that first thing you wrote as a model for the mirror, but then you would want a higher dimensional one, and that's why you introduce these U and V
Yeah.
variables. So
Yeah.
you get two.
Yeah, but
versions of
but
it.
as I think I sort of told you yesterday, like sort of, if you start, okay, so the like switching between this like Riemann surface and then this like higher dimensional thing is like personally very mysterious to me, but I can understand it in terms of like transition between like some sort of like derived bounded category of singularities here and like some like derived bounded category of coherent sheaves there, and they're going to have some isomorphism. So like both of them are the mirror in that sense.
Okay.
Yeah.
Okay.
But yeah, I'm happy to talk.
Is this what you're going to discuss in the secret?
No, it's not secret. It's not secret. But yes, that is part of what I plan to sort of recite what.
The homological merisymmetry
Yeah.
version of this.
It's just like me kind of reciting what Denis said to me poorly. So yeah, I'm going to do that at some point.
Denis said poorly?
No, I'm going to recite poorly what Denis said very well. Yeah.
When is this not secret event? That's
Sometime this evening, I guess.
Oh.
Yeah.
Not now.
Or it could be. I would prefer it to be this evening. Yes. Yeah.
Any more questions? So we'll meet again at 4. Let's think heavy.